Alright, so this is the first open whiteboard for units 9.1 to 9.3, which are about polar graphs. Polar graphs are a way of essentially graphing the magnitude and direction form of a vector rather than the component form. So for example, and I assume everyone already knows this kind of thing, we have it written like this, where we have the radius and then theta. So the radius, we go 3 out from the center along the direction of theta, right? So that point would be right here. Now this can be broken down into component form, and this is what the first 9.1 section is about, is essentially breaking this down into component form. Now some of these can be done using common triangles. For example, this is pi over 4, which you know is root 2, 1, 1, right? So this is going to be 3 over root 2, 3 over root 2 if we break it down into component form. But if we get down to it, it is really just r cos theta and r sine theta, where x is r cos theta and y is r sine theta. So inversely, if we want to go from x and y to r, we have several equations to do that. Now remember that r is essentially the hypotenuse because it's the magnitude, so we can do it like this, and this equation is important later. Or alternatively, you can do it like this. Though this is used a little bit less often. And then the same thing for r equals y divided by sine theta. So this is most of this first section. Sometimes you will see a negative number, sometimes a negative theta. Right, if we have a negative theta, you just go around this way. So for example, negative 2 pi over 3 is going to be here, because you go 2 pi over 3 from here. For example, with negative 2 pi over 3, you can add 2 pi to it to get 4 pi, which is how it would be if you go the other way. So sometimes you'll be asked to give multiple examples of a single point. So let's look at this with 3 pi over 4, right? Well, here, let me go back. Well, we might look at it like using this angle, right? So it's going to be negative 7 pi over 4 and 3. And then we can do similar things with the negative radius, which just flips it. So negative 3, 5 pi over 4. I assume all of you guys are mostly good with this stuff, right? This is pretty simple.
Mm-hmm. Yes.
Yeah.
So I think the one complex part, though it's not that bad, is the polar distance, right? Pole dist. I have this on my, I have the program that Ben made on my calculator, which is pretty fresh. I might put up a picture of it on here later so you can get it. I don't know if we can use it during
Maybe
the
I'll do a
test.
tutorial video or something.
Yeah, we can get a nice little tutorial. That would be nice. And I mean, the equation here, I'm also like someone to fact check this, but I believe it's r1 squared, r2 squared.
I think it's r1 squared plus r2 squared.
Is it r1 squared plus r2 squared?
Let me check.
I thought it was times.
Polar distance.
No, you're
Wow,
not.
yeah.
No, that's just fraudulent. Quinn.
Oh, it is. Wait, what's the equation? Because I actually don't know it. Tom knows it.
Yeah,
I
it
don't
is
know.
r1 squared plus. Okay. r1 squared plus r2 squared minus 2r1 r2 cosine theta 2 minus theta 1. And
I
this
hate
is
this
how.
formula. It's so
Yeah,
ugly.
this is how you
I
find
remember
the
it.
distance between 2 points in polar form. This is also how you solve this problem, but we're gonna do that in a little bit.
Jacob, do you think I should take the reference sheet or no?
Yes.
Should you take the reference sheet?
Yeah.
Well, we'll go over 9.2 next, and you can decide if you want to take it.
Okay.
So
Yeah, Quinn, just so you know, what I'm gonna do and what I always do is memorize as much as I can, and then I don't take it originally. But if I need to take it out during the test, then I'll do that and tell Mr. Fisher.
yeah, he
Okay.
always lets you take it out in the test if you feel like you need it. So 9.2 is shapes. So we got circles. We have limaçon. Right. For this, we have a excellent mnemonic from Ben Sadowski. We have the ICDC method. ICDC method. We have roses, and we have limniscete. Who knows how to spell it? I don't. Alright.
We have to
Said
know
he
how to
will not
spell
care
it. He said if you spell it wrong,
if you
you
don't
lose
have the
points.
reference sheet.
Oh no!
What?
Chance. Wait, he spelled it
serious?
wrong. He
Bro,
spelled
he
it wrong.
literally
and
Lemon.
put
said
it
It's
he
lemon.
wrote it as
Said it-
lemon.
He said to our
Lemon.
class that if you spell it wrong and you don't have the reference sheet, he will not take points off.
Oh, if you don't have it,
Lemniscete.
okay,
Yeah.
that's
Okay,
good.
this is lemon.
Let's try lemon.
Bro, this is an English class. You can't take points
Try to
after
push
that.
it. Try to push it as far as you can, right? Like
Alright,
lemon or
circle.
something like that.
Calm down. Yeah. How about you do that, Sam?
I'm gonna do that.
So, first we have circles. These have this form: a sine theta. Now, there are two alternatives for learning how to do this. The first one is to just like plot points, and then the second one is to memorize. So basically, you know a sine wave goes like this, right? And cosine wave goes like this, right? This is some new tech. So where the circle will be located is essentially whether A is positive or negative, right? So we have the 0 here, we have the 0 here. So if it's negative for sine, we know that's going to be 3 pi over 2. So this is our negative sine, this is our positive sine. And then for cosine, we see that around 0 it's positive, and around pi it's negative, right? So you can memorize that. I mean, this wasn't even really memorization. I kind of just looked at the graphs.
I think it's just
But-
easier to just kind of remember that it's like left and right for cosine and up and down for
Yeah.
sine.
That's good too. And the A is the diameter. So if I have an A of, and this is gonna make me count 1, 2, 3, 4, 5. If I have an A of 5, that means it's gonna be a diameter of 5. You need to remember that when you turn it from rectangular form, because this is
Yeah,
gonna
just
be
think
like,
that the A is the furthest point from the center.
yeah, this is gonna be like this, and then it's gonna be like 25. Or actually, it's not gonna be 25. It's gonna be 2.5 squared. Well, I don't care enough to calculate it right now, but it's so you gotta take. Well, first you gotta take the square root of whatever this is, and then you gotta double it to get A. So this is A, the absolute value. A. I mean, A can be positive or negative. That's what determines which direction it is. Alright. So, that's circles. I think everyone's pretty good with circles. So for Lumisol, we have ICDC from Ben, right? First we got the I, we got our inner loop. So this is the one they show on the thing. So when you're graphing lemniscates, or not lemniscates, limaçon, or really anything else, what you gotta remember is just look at the equation, right? They're gonna give you an equation for graphing them, and you can graph, if it's sine theta, you graph these 4 points. Actually, you graph these 4 points for all of them. And if it's sine theta, you're gonna want to graph pi over 6 and all these angles with the reference angle of pi over 6. And if it's cosine, you're gonna want to graph pi over 3. The reason why...
That's so you can get the nice 1/2.
Yeah, these are the nice 1/2. So for cosine, this is going to be 1/2. For sine, this is going to be 1/2. So this just allows you to approximate it with greater precision. Now there are other than the, here, let me get this down here. I need another polar. No, I gotta erase this too. Alright. But other than the limacon with inner loop, we have the cardioid, which is shaped like a heart. It's beautifully drawn. Then there's dimpled limacon, which looks the same. The way I drew it, it doesn't actually look the same. And then there's convex limacon.
That was a nice rectangle.
Come on. It looks
You
kind of
want
like
me to
this.
add an image of all of them from the reference sheet?
Yeah, you can add an image of all of them because it's going to be nicer than what I did. And you don't need to know this, but the distance, this distance is going to be a plus b. So how these are separated is the inner loop, a is less than b for I. So for the cardioid, a equals b, and in the equation a is the first one, b is the second one, and d, a is greater than b, but less than 2b. And for the last one, convex limacon, a is greater than or equal to 2b. So that's how you know the difference. This is the only way to tell without plotting points. And well, first of all, they're gonna ask you to name it on the test, and oh, here we got the limacon. Yeah, they're gonna ask you to name it on the test, and it just helps to know what kind of shape it is because then you know how it should look. Alright, I think that's it for limacon. So we got roses, right? Here, I need to keep like an extra one of these that I don't draw on. Oh wait. Oh, I'm getting so good at open whiteboard. Alright. So we got this, right? Roses are, you can have them as either sine or cosine. Now sine, you will have them usually centered around pi over 4 for the even signs, and then for odd, well, it depends. Often it's pi over 6, but can't believe
Sure, there's a way to calculate it. It's
yeah, well, it's pi over 6 for n equals 3. I don't know what, if it is. For
so basically, you set the sine, since sine pi over 2 is going to give you your maximum value. It's going to give you 1. Sine pi over 2 is going to equal n times theta, and so you divide sine pi over 2 by n, and so that's whatever.
Yeah. So
what?
n.
You divide pi over 2
If n
by
is
n,
odd,
whatever.
then the rose has n petals. So like if we have a sine 3 theta, you're gonna have to graph it looking better, but it has 3 petals, right? If it's even, it has twice as many petals, and each petal is going to be exactly mirrored by a petal on the other side. So you only have to do 1 petal for each one, because you can do an exact mirror of it on the other side. There's often other ways that you can look at this symmetrically. The way to be the most safe when doing these is to plot all your points. It's the same as with limacon. You want to use these extra points to make sure that you're good when drawing these. He said will take off like half points if they don't go through the extra points, even if you don't need to actually draw them. Alright, so the last one, and Mr. Fisher says the easiest one, is a lemniscate, which has the form r squared equals a squared cos 2 theta, or sine. And essentially, if it's cosine, it's gonna look like this, wrapped around the, oh my gosh, wrapped around the, it's gonna look like this but better, okay, I promise. Let's see, can I get it? No, I cannot draw on the whiteboard still.
Another image.
It's centered around, yeah, you can put in an image. It's centered around 0 and pi. For the sine one, it's going to be centered around pi over 4. And it's just like a 2-petaled rose. So, you know, you have a squared, so you got to watch out for that, because usually all you see in the equation is r squared, because an a squared is a numerical value. But if you take the square root of a, that is how you find the distance from the center out. And this is the only point Mr. Fisher says we need. Make sure that it rounds out around the top. So like, roughly like this. That's actually a pretty good one. I guess I figured it out. And then this distance is going to be a. Alright, do we have any questions on 9.2?
Oh yeah, Jacob, can you go over where the rose petals are centered depending on whether it's sine or cosine?
Okay, so when we have cosine, okay, so first thing I'm going to do for evens, so for evens, when you have sine, they're all going to be centered around the pi over 4, and when you have cosine, it's going to be centered around 0. Like on the lemniscate.
Okay.
Now I believe that for r, a cos 4 theta is the same as r a cos a sine 4 theta, because at that point you have 1 at each of these 4 points.
Right.
And
Okay.
it just becomes the same. Then for n equals 3, for the sine variation, it's going to be centered on, this is not pi over 6. Pi over 6 are 30 degrees, because the maximum should be at 90 degrees, but it's 3 theta, sine 3 theta, so just divide it by 3, you get 30 degrees.
Oh, wait. Okay, I see why that is. Because you want it to be equal to 1.
Yeah, so when you plug in points in this, right, you know you want like 30 degrees and 90 degrees, so just divide
Right.
those by 3. For example, you can use 10 degrees, and that allows you to get more points.
Okay, I get that now. Thank you.
Alright, and then spiral of Archimedes, they're weird, but he says we don't have to do them, so that's nice. It's like this. They're really weird. Alright, are we good on 9.2?
Yep.
Alright, so for 9.3, it's a lot less of theoretical stuff and a lot more of like the identities we know, and using these things properly. R cos, including r cos theta equals x, r sine theta equals y. So remember, this whole section is about transferring equations from polar to rectangular and vice versa, where before we were working on things transferring points to polar and rectangular and vice versa. Now this is around equations. So I feel like there's not much theory in this one other than, you know, these fundamental equations, and then you also should know the things like the sum of angles, right? So cos theta, I don't know why I wrote cos theta x plus y, it should just be cos x plus y. But that's gonna be cos x, cos y, and let's make this plus or minus. Minus plus sine x, sine y. And for sine x plus y, it's going to be sine x cos y plus or minus cos x sine y. So we need to know these for identities. We also might need the double angles. Here, I don't actually remember these off the top of my head. So it's like sine 2 theta equals plus or minus square root of and is it 1 minus, here, remind me what this is again. I don't remember. It's like 1 minus cos theta over something. Let's look it up. Double angle identities.
Yeah, it's 1 minus cos over 2.
Yeah. Oh, so I actually did get it right. That's amazing.
Also, wait, what would we use the addition or whatever, the summer difference formulas for? Like
So you use these. Actually, did you do the homework problems? Because there were some where we used those in there. Like, you'll just
I
get.
don't remember the homework.
You'll just get stuff like r equals 5 secant theta plus pi over 3 or whatever. And you'll just have to use these. You know, and you need to know these kinds of identities to transform secant, for example, into cos. And so then this, you simplify it into this, and then you multiply it over, and then because you're going to have all these r cos theta and r sine theta, you turn them back into x and y. So that's an example problem where you'd use these. That makes sense?
Yeah.
But you're going to have your calculator for this whole section, which makes it a little bit easier. But I think this is still some of the harder stuff. So, do we have any questions on 9.3? Or the big 9.3 up here? Alright. I'm gonna... Oh, how do I resize this? I wanna make this bigger. I'm gonna do some of the questions for the 9.1 to 9.3 quick review before I end the video. So, right, there's some of the answers here. Just kind of ignore them. So this first one I think is the hardest. It uses the polar distance, right? So it says that we know the polar distance equals 5 equals r1 squared. So r1 squared is 3 plus r2 squared, which is 4, and then minus 2 times r1 2 times r1 times oh well, I didn't write that 2 in there, didn't I? Oh, wait, I wonder if I can use the lasso here. Oh, that was sneaky. And then you got times cosine theta 2, which is going to be 7 pi over 9 minus theta. So we've set that equation up right. Let's make sure. Yeah, I think that is right. So then let's simplify in here. We can square both sides, so we can have 25 equals 25 minus 24 cos 7 pi over 9 minus theta, but I'm just not going to write it because it's going to go over the problem. And we can subtract and then divide, so this is going to end up being 0 equals cos 7 pi over 9 minus theta. And like once again we got to use the summer difference formula. So we got to say that 0 equals cos 7 pi over 9 cos theta plus sine 7 pi over 9 sine theta. Alright. Everyone following along here?
Yep.
Okay, I gotta put my calculator in radians. I almost lost the whole thing there. Okay, so we get, and tell me if you get this, I got 0.643 sine theta and negative 0.766 cosine theta. Alright, do we get this?
I don't have a calculator out, but that looks good.
Wow. Okay, so let me make sure this works before I do the last step, because I'm sure I've done something wrong in here, because this is a hard question.
I got the same values.
Oh, let's go. That's nice. And yeah. Alright, so this works when I plugged in the thing. So I think what we're supposed to do here, actually, is, well, this is how I would think to solve the problem, is to multiply this whole thing by the reciprocal of one of these numbers. Like, let's pick 0.643. So that's gonna make it just sine theta. And then let's switch around the equation a little bit to make it a little bit easier. And then minus 1.19 cosine theta equals 0. And we can do sine theta equals 1.19 cosine theta. Alright, and we can do 1 equals 1.19 cosine theta over sine theta. Actually, let's do this the other way around. I changed my mind. You'll see why in a second. Sine theta divided by 1.19 cosine theta equals 1. So that's going to be...
Is it because you want the sine over cosine?
Yeah.
Yeah.
Tan theta equals 1. Wow, I wonder if I could have done this any better way. Alright, let's see. And that gets me... And that gets me 0.8. So we're going to do arctan 1.19, which gets me 0.872. Now he said we could express our answer as a decimal for this. And my 0.872...
18 is 0.87.
Yeah.
There's definitely a much easier way.
Well, you can find it, but I think this is a relatively difficult process. I mean, there are definitely different ways
just
to
for this
solve
problem specifically.
algebraically.
For this problem specifically, you realize that the cosine has to equal 0 if 25 equals 25 minus 24 cosine, whatever. And so no, it has to equal 1 or whatever.
Oh, this has
Right,
to...
no, it
yeah,
has to
you
equal
could
pi
do
over
this
2.
equals 0, that's true.
Yeah.
But look, I got my answer anyway, and now you're sad. So yeah, if you did that this way, this would be a lot faster. 0 equals cosine 7 pi over 9 minus theta, and we know that cosine is 0 at pi over 2. So we say that 7 pi over 9 minus theta equals pi over 2. And then that becomes a lot simpler, doesn't it? And yeah, now we see where we got the 18 in the denominator too, because you get the 9 pi over 18, subtract, you get 5 pi over 18 minus theta equals 0. 5 pi over 18 is theta. Yeah, so this is faster. That's true. Alright, let's do the other ones here. So this one, you can kind of just look at it, right? You know that the diameter is 2. So it's going to be -2, right? Because we see it's on the left. And it's cosine theta because it's on the horizontal instead of the vertical axis. So really, I mean, I know the thing is right there, but you can kind of just look at it. For this one, theta equals 3 pi over 4. You can visualize it like this here, right? And negative x, as they say. And yeah, it's a line. And this one too. Okay, let's ignore this for a second. So this one has the center at 0, -3, with a radius of 3. So we know that it's going to be down here, and that A is going to be 6, right? Because we know that A is the diameter, which is twice the radius. So because it's down here, we know that it's going to be negative sign, because sine is along the vertical axis and this is in the negative direction. So we can just write -6 sine theta. So for these, make sure you do all the stuff it asks you to, like identifying the graph here, like this is a line, this is a circle, and drawing on the polar thing. But I feel like if you just know how to recognize these circles and just transform them just off the top of your head because you know the formula, it's a lot easier than trying to work with, you know, the r cos theta, r sine theta stuff every time. Alright, I'm gonna end the recording here. I think this is pretty good. Do you want any questions before I stop recording? Alright. Say goodbye.
Goodbye.
Goodbye.